Okay, looking at integration by parts here, and this is undoing the product rule. All right, integration by parts is kind of a tricky part, but if we're going to talk about integration by parts or doing the product rule backwards, let's very quickly revisit the product rule. If you remember the product rule, f times g, the derivative is f prime times g plus f times g prime. So there's our product rule that you should know by now. God help us if you don't. Okay, the product rule, if I can do the derivative and get this answer, then that means I could, therefore, do the antiderivative of all of this. And if I do the antiderivative of that stuff, I will get this as an answer. So we're just kind of going in the opposite direction. So that's what we're going to do for integration by parts. Except I'm going to do a little bit of magic to this before we see our parts formula. I'm going to split this antiderivative up. Instead of the integral of two things, I'm going to split it into two integrals of f prime times g plus the integral of fg prime. It still gives you the original product that we started with. And then I'm going to go crazy, and I'm going to take this integral right here, and I'm going to move it to the other side of the equation. I'm just going to take it and stick it right there. And when I do that, it becomes this antiderivative equals f times g minus the integral of f prime g. Or another way you could write that so there's not as much parentheses and stuff, and this is how a lot of books will describe parts, the integration by parts, is the integral of uv prime equals uv minus the integral of u prime v. It's kind of breaking some rules of math because I don't have a dx or a du or anything in those antiderivatives, but that's kind of the short formula that we will use, and these are your formulas for integration by parts. So these two things right here are what you need to remember when we are doing integration by parts, because that's our formula. All right. Now you may be noticing this is kind of bizarre because you're starting with an antiderivative when you do integration by parts. We start with an antiderivative, and the answer also has an antiderivative. Well, this is not really the final answer. Our goal is to look at our integral, and this antiderivative would be something hard, something you can't do, and when you work out the formula, hopefully this one would be something that's a little easier to do. So the is a different integral or antiderivative that's a little bit easier. So let me erase that, and let's try one problem using integration by parts. Well, let's see. Let's try one real quick. Here is the antiderivative of x times sine x. When I'm doing antiderivatives, parts is not the first thing I look for. I will try to do, see if it's something I recognize, like maybe it's an inverse trig derivative, or maybe it's a power rule, or maybe even use substitution, do an integration by substitution. Unfortunately, all of those fail. I do see a product. It's x times the sine of x, which kind of makes me think we may need to use parts. So I'm going to try parts here, and when we do parts, I'm following this formula right here. I need to identify a u, and I need to identify a v prime. In this problem, I'm going to pick u to be x and v prime to be sine x. And as I start working this out, I'm looking at my formula. I have a u and a v prime. My answer, when I set this up, I need a u times a v. I already have u, but in order to get v, v prime is sine x, and I guess the dx needs to go with it. I will anti-differentiate. I'll integrate both sides of this thing. So the antiderivative of v prime is going to be v. And the antiderivative of sine x dx that would be negative cosine x dx. So there's my v, but then I also need u prime. So I'm looking over here at u prime, and I'll just simply do the derivative of this, and the derivative of x is 1, and technically it's 1 dx. Whoops, that dx doesn't need to be there. Okay, so now I'm going to start working out my formula. So this thing is going to become, it's going to become u times v. So u times v, I multiply those two, so that'd be negative x times the cosine of x, and then minus the antiderivative. So I multiply those two, and then I subtract this product. So minus the antiderivative of 1 times negative cosine x. dx. I will, just for the sake of making this a little bit easier, I'm going to pull this negative out right here, and I'm going to turn it into plus the antiderivative of cosine x dx. And the goal, if you remember, is to take an ugly antiderivative and use integration by parts to create an easier antiderivative. And the antiderivative of cosine x is very nice. I know how to do that. The integral of cosine x is simply sine x. So I'll bring everything else down. Negative x cosine x plus, and that antiderivative is sine x. And we have to remember plus some constant. So there is our answer for this one. Good. So you pick a u, you pick a v prime, and then you do find u prime, you find the antiderivative of this one, and then you plug into your formula for integration by parts. Now this problem, I want to show you what happens real quick. I'm not going to spend a whole lot of time on this. What happens if you choose the wrong thing for u and v prime. So let me copy that. And let's see what happens when I choose the wrong thing for u and v prime. Let's say that I picked sine x to be u, and I picked x prime to be, or not x prime, I picked x and the dx to be my v prime. Well, then when I do my derivative, the derivative of sine x would be cosine x dx. The antiderivative of x would be 1/2 x squared. And then I'm going to put that into my integration by parts formula. All right, there we go. I paused it and worked it out real quick. If you look at this, when I choose a different u and v prime, I started with x times sine x. I ended with x squared times cosine x. I created an uglier antiderivative that actually is worse than what I started with. So that's what happens when you choose the wrong thing for u and v prime. Sometimes when you choose the wrong thing, your v prime cannot be integrated. So you kind of hit a brick wall at the very beginning. So there is a little mnemonic device that will help you determine what to pick for u when integrating by parts. By the way, this has nothing to do with u substitution. This is a different kind of u. But I use the expression liate. I can't think of anything q. Y'all can create a sentence for that. But I just say liate. And these are the things you pick for u in order. First, if you have a logarithmic function, like y equals ln x, so logarithmic, if you have ln x or something like that, then you would use that for your u. If there's not a natural log or any logarithmic function, then you look for inverse trig, anything like arc sine of x or arc cosine of x or anything along those lines. Okay, if there's not an inverse trig, then the next one you go to is algebraic. Now, algebraic means just something like x or x squared or the square root of x, x to the -3, anything like that, x to some power. Those are your algebraic functions. That's what you would choose next, and that's what we did in that first example. There was no log function, there was no inverse trig function, and the one that worked is when I chose u to be x. If there's not an algebraic expression, then you want to choose a trigonometric expression for u, which would be something like sine x or cosine x. Now that is different than inverse trig. And if you don't have any of those, if all you have is an exponential function, then you would pick that for u, but honestly, you wouldn't ever pick this for u. By the way, exponential means something like e to the x or a number to the x. Those are exponential functions. So that's how you decide what to pick for u. Start with log, then inverse trig, then algebraic, then trig, then exponential. So let's try that with a few problems. We're already 9 minutes in. Let's see. Let's try this one. We have x times the natural log of x. And remember, I like to use the little liate expression, L-I-A-T-E. And there is a logarithmic expression. There's ln x. So that I'm going to let my u be the natural log of x, which means my v prime would have to be what's left. Now, one thing that you need to be aware of, when you're choosing your u and v prime, when you multiply these two things together, when you multiply your u and v prime, they have to multiply to give you your original function. And they do. If I did ln x times x, it does give me my original function. So you have to make sure that everything is down here in your u and v prime. Okay, so let's see, the derivative of u, I need to find u prime. that would be 1 over x. The antiderivative of x, the antiderivative, my v, is going to be 1/2 x squared, or you could say x squared over 2. And then our formula for integration by parts, we do u times v, so that will be 1/2 x squared ln x minus this product. So minus the antiderivative of 1 over x times half x squared. That's the same thing as x squared over 2 dx. And I still have a product. That's not very nice looking as it is right now, but 1 over x times x squared over 2 does clean up. This x will cancel with one of these, leave me with the antiderivative of 1/2 x dx. The 1/2 x squared ln x, I'm just going to bring down for the rod. Minus that. And then I will pull this 1/2 out here. That's a constant. I can pull that out of the antiderivative. And now I've got 1/2 x squared ln x minus 1/2 antiderivative of x dx. And then finally, I'm going to do this antiderivative, the integral of x dx. That's going to be x squared over 2. And everything else is just going to come down for the rod. So that'll be minus 1/2 and the 1/2 x squared ln x. And then don't forget the plus c. So there's our final answer. Good, good? Good, good? Take your u and your v prime and then work out the formula. Let's try. Let's see what's next. X e to the 3x. Okay, let's see. Let's think about Liate. L-I-A-T-E. There is no log function. There is no inverse trig function. Algebraic, that's what x is. X is my algebraic function. So I'm going to let u be x. V prime is going to be e to the 3x. Then I need to find the derivative of u. U prime is 1. The antiderivative of v. The antiderivative of e to the 3x is e to the 3x divided by 3. And then I'm going to put this into my parts formula. U times v, which is x e to the 3x over 3, minus this product, 1 times e to the 3x over 3, so minus the antiderivative of 1 times e to the 3x over 3. Just like always, I like to pull out my constant. There is a divided by 3, so I'm actually going to pull that out and change this integral, change that to 1/3 antiderivative of e to the 3x. Everything else is going to come along for the ride. And now finally I'll do that antiderivative. So x e to the 3x over 3 comes down minus 1/3 times, and then the antiderivative of e to the 3x is e to the 3x over 3 plus some constant. Good, good? Good, good? Good, good? Good, good? Good, good? Good, good? All right. Let's see. Arctangent x dx. Now this is one that confuses people. People don't like this because they only see one thing. The things that I see that trigger parts in my head is a product. Like here I had x times e to the 3x. For number 2, I had x times the ln of x. For number 1, we had x times the sine of x. By the way, this was a huge fail. I picked the wrong view there. So when you see a product, that triggers parts. When you only have arctangent x and nothing else, it may not be screaming parts. And so let's see what we can do here. So we have, let's see, arctan x. I don't recognize that. I know the derivative of arctan. I don't know the antiderivative. I don't see any u substitution that's going to work. Power rule definitely isn't going to work. So I'm going to try parts simply by default. Everything else has failed. So I'm going to try something for parts, u and v prime. And remember, Liate, L-I-A-T-E, there is no inverse trig function here. I'm sorry, there is no log function, but there is inverse trig. So I'm going to let the arctan be my u, which means, well, that's gone. The only thing left is dx. so dx, or you could, if you want to, say 1 times dx is my v prime. The derivative of arctangent is 1 over 1 plus x squared. The antiderivative of 1 is just x. And so when I do parts here, I will have x times the arctangent of x minus this product minus the antiderivative of, and that would be x over 1 plus x squared. Okay, so now I've got x arc 10x. Now I need to tackle this, and when I see a fraction, my eyes are immediately drawn to the denominator, and I know that, let's see, I have 1 plus x squared. The derivative of that is 2x. If I put a 2 up here, I'll offset it with a 1/2. My top is now the derivative of the bottom. If you can get your integral so that the top is the derivative of the bottom, then the answer is going to be... Hey, I just paused the video for about 20 minutes to go do something, and now I don't remember where I was. I'm guessing at this point I was pointing out that the top is the derivative of the bottom, and that's how you do the derivative of logarithmic functions. So the answer to this integral would be 1/2 on the outside, kind of hangs there for, goes along for the ride, and then it's 1/2 of, this whole thing would be the derivative of ln 1 plus x squared. Don't forget the plus c, and then all of this stuff on the front also comes down for the ride. So x or 10x minus all of that. So there we go. Let's try this one, x squared e to the x. And I believe this is the last one I wanted to do, although I'm going to show you 2 ways to do this one because this does something interesting. Let's see, we have liate, L-I-A-T-E. There is no logarithmic function. There's no inverse trig function. There is an algebraic function in x squared. And before I set up the parts, one thing that I want to point out is I don't always just dive straight into parts. Usually I will look for substitution. And this problem can be a little bit misleading because some people may be thinking, oh, let's try normal u substitution, where u is going to be x squared and du would be 2x dx. And you may be looking at this thinking, let's see, I need to find my 2x dx. I have an x dx. If I put a 2 there, you may think that creates a du, but the problem is that's 2x in an exponent. It's not 2x times the dx. So regular u substitution fails, but always be on the lookout for it because every once in a while, when you think you're going to do parts, substitution actually works. So anyway, back to parts. So I'm going to try u, and I'm going to try v prime. My u will be the algebraic term, x squared, and my v prime is going to be e to the x. Now I love e to the x because I can do that all day long. The antiderivative of e to the x is e to the x. The derivative of u is going to be 2x. And then when I plug that into my parts formula, that's x squared times e to the x minus the antiderivative. Oh, that was a horrible antiderivative. Much better. Minus the antiderivative of 2x times e to the x. And then we look at that antiderivative, and we hope that that antiderivative is easier. The problem is, even though it is easier, that e is just really bugging me. There we go. A little worse than what I started with. There we go. All right. So I did parts, and now I have 2x e to the x. I suppose I could, just to make myself feel better, bring that 2 out, because that is a constant. And if I pull that 2 out, I now have x squared e to the x minus 2 antiderivative of x e to the x. The problem here is I now have another product, although it's slightly cleaner than what I started with. I started with x squared. I did parts. I ended up with x to the first. But what I've actually created is a second parts problem. One parts problem did not completely clean this thing up. So now I need to do parts again in order to work out this antiderivative. So let's see. I would pick a u, the algebraic term, which is x. I would pick a v prime, which would be e to the x. and then we'll work this out with parts. The derivative of x is 1. The antiderivative of v is e to the x. And so this, I'll do u times v, so that'll be x times e to the x minus the antiderivative of 1 times e to the x. Good, 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 good. And then all of that is being multiplied by this net minus 2 right here. So I'm going to bring down my x squared e to the x minus 2. It's minus 2 times all that. So then I'm going to continue cleaning up what's inside these brackets. X e to the x doesn't really do anything. Minus the antiderivative of e to the x is e to the x. And then the other stuff down front is going to keep coming along for the ride. X squared e to the x minus 2 times all that stuff plus c. And there we finally have our answer. So we actually had to do parts twice on that problem. In the cases where you can do parts twice, there is a trick that sometimes you can use to wipe out the whole problem in one big swoop, and it makes it a lot easier. And it actually works in this problem. So let's try this one again, and we're going to set up parts. So we have u to be x squared and v prime to be e to the x. All right. This shortcut works only for algebraic u's, if your u is an algebraic expression, and you can take the derivative all the way down to 0. If I take the derivative of x squared, I get 2x. If I do the second derivative of x squared, I get 2. If I do the third derivative, I get 0. And that is a good thing. You want your derivative of u to be able to go all the way down to 0. Because if you can do that, there's a cute little shortcut. And the way the shortcut works, however many times you did the derivative, you need to do the antiderivative just as much. And the nice thing is I can do the antiderivative of e to the x as long as I want. So the antiderivative of e to the x is e to the x. The next antiderivative would be e to the x. The next antiderivative would be e to the x. Now I've kind of violated some notation rules because I had v prime, then I just kept writing v. I guess if I went all the way down to the third derivative, then I need to treat this as the third derivative of v. This would be the second derivative. This would be the first derivative. And this would just be v. Although I'm not going to be too picky about how you write that notation. The way the shortcut works is we start off almost exactly as we did before. We start off doing u, and we go down to, in this case, to v double prime. But that would be x squared, e to the x. And your first one is always positive. I could have been writing that little plus sign, and I'm just writing that plus to remind me that it's a positive product. And I've been doing the positive product all along. I did x squared times e to the x, and I didn't change any signs. Same thing here. I did arc10 times x. I didn't change any signs. So I start off doing positive, and normally we go straight to the left. But instead of going down to v prime and then straight to the left on this shortcut, we keep moving down diagonally and we alternate signs. So I'm going to do u prime times v prime. I'm going to do u double prime times v, and you alternate the signs of the product, and that would give me x squared e to the x minus 2x e to the x, and then plus the product of 2 e to the x. And then you actually don't even have to use the last line. That's your answer. That is the full antiderivative. If you don't believe me, go back and compare this answer to what we just did. And you'll see that it is the same. All I have to do is distribute this negative 2. If I distribute that negative 2, I get negative 2x e to the x plus 2e to the x plus c. And that is the same answer we just got right here. The only time you have to throw an antiderivative in your integration by parts is if you multiply straight left and right. So if I wanted, I could have gone crazy and done this last little step and said minus the antiderivative of 0 times e to the x, right? And the antiderivative of 0 would be just some constant. And so technically that's where the plus c would come from. But we really don't need to think about that. This video has gone on long enough. I knew it was going to get long. I was hoping to keep it under 20, but I failed miserably. All right, that's good enough.